Welcome to The Explainer. Today we're digging into a really powerful idea in artificial intelligence called multitask learning, or MTL for short.
So, here's the plan. We'll start with a simple analogy, get a clear definition of what MTL is and what it's not. Then we'll see why it's such a big deal. After that, we'll hit a major real-world problem and how researchers are thinking about it. All right, let's jump in.
Okay, so to really get our heads around how a machine learns a bunch of things at once, it helps to start by thinking about, well, how we do it.
Think about this for a second. If you know how to play tennis, how does that help you learn squash? Well, a lot, right? You've already got a feel for the swing, the footwork, that hand-eye coordination, all that stuff transfers over. And that basic idea, using what you know from one skill to get better at another, that is the absolute core inspiration for multitask learning.
Okay, so that's the human side of things, but what does this actually look like for an AI? Let's nail down a clear definition and, just as importantly, see how it's different from a few other big ideas in machine learning you might have heard of.
So here it is. The key word you really got to latch onto is jointly. The AI isn't learning one thing, then another in isolation. No. MTL systems are specifically designed to find and use the shared patterns between different jobs all at the same time. Just like we instinctively find what's common between tennis and squash, the AI does the same thing, using that shared knowledge to get better at everything it's doing.
Okay, now this is where things get really interesting, especially when you compare it to something called transfer learning. I love this analogy. Think of MTL as a study group. Everyone's at the table, sharing notes, and everyone gets smarter together. All the tasks are treated as equals. Transfer learning, though, that's more like a senior mentoring a freshman. The knowledge mostly flows one way, from the experienced task to help out the new one.
And hey, don't mix it up with multi-label learning either. They sound similar, but they're not the same. With MTL, you could have, say, one huge data set for predicting patient health and a totally separate one for predicting stock market trends. The AI learns from both at once. But with multi-label learning, it's all about one data set. You've got one photo and you're just slapping multiple tags on it, like dog, park, and sunny. See the difference? Separate tasks versus multiple labels for one thing.
And one last thing to clear up, it's not multi-view learning either. Multi-view is all about tackling a single problem, but from different angles, like analyzing a news story by looking at the text and the images that go with it. MTL, on the other hand, is all about solving multiple, distinct problems at the exact same time.
Okay, so we've got the definition sorted, but why should you care? Why is this such a big deal? Let's move from the theory to what this actually means in the real world.
Right. This is where MTL really becomes a total game changer. It's so powerful, especially when you're in a situation where you just don't have enough data for one of your tasks. The model can actually borrow strength from the other, more data-rich tasks. And what does that do? Well, it makes the whole system way more accurate and way more reliable. And this isn't just theory. It's crucial for things like self-driving cars that have to spot pedestrians, read signs, and see other cars all at once. Or think about medical AI that could spot multiple diseases from just one set of patient data. It's huge.
But it's not all smooth sailing. There's a pretty major hurdle here. You see, the classic theory behind MTL, it made one giant assumption, an assumption that, it turns out, almost never holds up in the real world. Those early models, they kind of just assumed that every task you're teaching the AI has more or less the same amount of data to learn from. But let's be real. What happens when that's just not true? What happens when some tasks are giants and others are tiny?
And this table just lays it out perfectly. Look at this. An AI system could be swimming in data for task A, 10 million examples of ad clicks for a huge client. But then, for task B, maybe a super important medical prediction for a rare disease, you've only got 500 samples. And for task C, trying to spot fraud for a brand new product, maybe just 50. This is what we call the unbalanced setting, and it is a massive problem.
Yeah, this imbalance is a beast of a challenge. And this quote from Zaccarini and Lampert really hits the nail on the head. All those nice mathematical guarantees we had for how well MTL works, the fast rate bounds they talk about, they just go out the window when the data isn't balanced. The model gets completely overwhelmed by the task with 10 million data points, and it can basically just ignore the little guys. So you could end up with an AI that's a world-class expert on ad clicks, but is totally dangerously useless at spotting that rare disease. The old rulebook just doesn't work.
So to fix this, researchers had to take a step back. They realized they needed a totally new way to even think about what success means when you're dealing with this kind of mess. And this led them to this really fascinating, really critical fork in the road. On one hand, you have the task-centric view. This says every single task is equally important.
Think about healthcare. You want the best prediction for every patient. It doesn't matter how rare their condition is. Every customer gets the best possible experience. On the other hand, you've got the sample-centric view. This approach says, let's just make the most correct predictions overall. And of course, that's going to favor the tasks with the most data. This might be what you want if your main goal is just maximizing ad revenue across your biggest clients. So you see, there's no single right answer. It totally depends on what you're actually trying to achieve.
And this isn't just a technical detail. This choice, it points to a much, much deeper question we all have to face as we build these incredibly powerful AI systems.
So we've seen how multitask learning helps an AI learn more efficiently, kind of like how we do.
But the real frontier here, the real challenge, it isn't just about making AI learn more stuff. It's about making it learn fairly.
And that really is the heart of it, isn't it? Deciding between a task-centric or sample-centric approach, that's not just some technical choice you make on a whiteboard. It's a deeply ethical one. It's a choice that determines whose problems get solved and whose get ignored. So the really big question we're left with for everyone building and using this stuff is this. As AI gets better and better at learning, how do we make sure it's learning the things that reflect the true diversity of our world and not just the things we happen to have the most data for?